last speaker today, Carlos Simpson from the University Nice is going to give a talk on high Kodaira-Spencer map.
Okay, so thank you very much. Thank you very much to the organizers, to Stephen, Kong, I guess Mao maybe, for organizing the conference. Very interesting. So let's see. Well, okay, so what I would like to do today, so what I've actually been working on the last year has been computer stuff mostly, and that would be kind of off topic for the conference. Plus the local system stuff I've been working on the last year. I already gave a talk about that in the conference last year in Hefei, organized by Kong and Mao. And we've made a little bit of progress, but pretty technical, I think. So I wouldn't be prepared to discuss that currently. I mean, more than just redoing the talk from last year. So I didn't think that would be very interesting. So what I decided to do was to go back and talk about some work from some time ago. So dare I say I'm improving on Bruno's result by talking about a preprint that's been on the archive for 23 years. Sorry, Bruno, but yeah, so I'd like to talk about this preprint on secondary Kodaira-Spencer classes and nonabelian Dolbeault cohomology. As I said, that's really from some time ago. But I think it might be topic, so I'm hoping it will be interesting for the conference because I think it should be somewhat topical for the conference. So that's the idea. Okay, so let's just talk. So this is going to mostly be sort of recalling lots of different setups and stuff like that. So let's recall for the Hodge filtration on usual abelian cohomology. So we take a stack. Usually we just take the stack, the affine line, and then think of things as being GM equivariant over the affine line. But we can define a stack, which is the quotient of the affine line by the scaling action. Then, so an object over this script A thing, it's just a GM equivariant object over the affine line. And so so the origin is 0. So as a substack, the origin is actually a classifying of GM. So that means that an object over 0 is going to have an action of GM on it. Then there's 2 points. There's 0 and 1. 1 is the orbit of the point 1 in the affine line, and there's no stabilizer. So 1 is just a point, and 0 is a point that has the structure of VGM. Now, if we have a smooth projective variety, of course, I mean, we've seen some stuff about parabolic structures that maybe you could use for the quasi-projectives case, but let's just stick to the smooth projective case. So if we have a smooth projective variety, then we get a formal stack, which we'll call X Hodge, mapping to over A. Okay. So I think you've all seen this before, maybe. So the fiber of X Hodge over 1 is the Durham stack, defined by X Durham of Y is X of Y reduced. So this is a sheaf on the side of schemes over K. So K is going to be a field of characteristic 0. I think I said that a few slides from now. So this is the quotient of just the sheaf X by an equivalence relation, which is the formal completion of X cross X along the diagonal. So that's a formal scheme contained in X cross X. And this comes from, so I should maybe say, sorry, I didn't write on the slide. This comes from Grothendieck's point of view on crystalline cohomology as viewed. So I guess I learned about this in Berthelot's big, gigantic yellow book. So if you read Berthelot's book on crystalline cohomology, but you don't actually understand anything about characteristic P, then what you get out of it is basically this idea. Okay, so in other words, we have a formal, what's called a formal groupoid. That's the completion of X cross X along the diagonal. Then we can take the quotient of X by that equivalence. It's a formal groupoid, but it's an equivalence relation because it's mapped to X cross X is injective. So so the quotient is just a sheaf rather than a stack. But if you had a formal groupoid, then the quotient in principle would be a stack. So, and that's what happens in the fiber over 0. Okay, so in the fiber over 0, the stack, it's something similar, but instead of taking the formal completion of X cross X along the diagonal, we take the normal cone of the formal completion, which is to say the tangent bundle of X completed along the 0 section. So the fiber over 0 is what we'll call X Dolbeault. So that's the classifying stack of the formal completion of the tangent bundle along the 0 section. So as we'll see later, this, I mean, let's just think, roughly speaking, this is just the classifying stack of the tangent bundle of X. The fact that we did this formal completion doesn't change too much for us. Okay, and this has an action of GM, which is just by scaling on this vector bundle. So this is just an abelian group scheme over X, and we're taking the classifying stack over X. So maybe I should have said X Dolbeau maps to X, which is not the case for X Duran. X Dolbeau maps to X. Okay, so in this X Hodge, well, it's a formal groupoid. You can define it by sort of taking the deformation to the normal cone. If we take the deformation to the normal cone of the Duran formal groupoid, then you get this. That deformation is the formal groupoid over the affine line, and it's GM equivariant. So we get this X Hodge, which is a formal groupoid. And we can think of that as representing a simplicial presheaf on the side of K schemes, such that the values of the presheafs are one groupoids. And over, there's spaces whose fundamental group is something and which don't have higher homotopy groups. That's what one groupoid means. And in fact, over 1, we have a sheaf of sets, so it's a 0 groupoid. And over 0, we have a groupoid. Let me just go back. The groupoid is the B of Tx half. Okay, and then we can take cohomology relative to A. So we can take the cohomology of X Hodge over A. So this means, Ri, pi lower star or something kind of thing down to A. And we get a system of vector bundles over A, the script A. So let me point out that this O, so we should really think of O as being sort of like a D module, basically. Because if you take a sheaf on X, if you take a sheaf over X Duran, that's the same thing as a D module. And so the sheaf O as a D considered as a D module, that's the constant coefficient system. So we can take the cohomology of X Hodge over A with coefficients in the constant coefficient system, which is the structure sheaf. So we can think here of, well, I just write O as it's actually just the structure sheaf of this big side of schemes over K. Maybe we should say something about Noetherian or finite type or something like that. But basically, schemes over K. And then when we take the relative cohomology, we get a system of vector bundles over A. Now, a vector bundle over A is a filtered vector space. This is the Rees module construction, which would be related to the computer stuff I'm doing, curiously enough, by some long roundabout relationship. But this guy Rees, I guess he was doing semigroups and filtered rings and so on. So anyway, okay. So a vector bundle over A is a filtered vector space whose underlying vector space is V1 and the associated graded is V0. The filtration is obtained by taking GM invariant sections and looking at their order of growth as we approach 0. Okay, so, and then in this, if we take V equal to this cohomology, then the V1 is the Duran cohomology of X, which is the hypercohomology of X with coefficients in omega dot XD. This is the crystalline cohomology theory just in characteristic 0. And the associated graded space is the Dolbeau cohomology. So the cohomology of that classifying stack is going to be this thing. It's going to be the direct sum of HQ of X omega PX. That's basically Koszul duality, right? Because the tangent bundle is spec of a symmetric algebra, and the cohomology is going to be spec of the exterior algebra. Okay, and the GM action is by scaling by T to the P on HPQ. HPQ being this thing. Okay. So now suppose we have a.
Could you repeat the definition of A? I'm sorry.
Sorry. So A is it's that quotient.
So okay.
Using the same letter, so you can just think of A as being A1 if you like. Okay.
Okay. No, that's okay. Yeah.
So A is A1, but we're looking at a GM action. So we're looking at GM equivariant things over A.
Okay.
This is the Rees module. So if you have a vector bundle with a filtration, if you have a vector space with a filtration, and you do the Rees construction, you get exactly a vector bundle over this script A. Okay.
Thank you. Sorry.
The Riesz construction means, you take basically you do sort of the elementary transformation of your space along that filtration at the point 0. That's going to be GM equivariant, and it reflects the filtration. So that's roughly an equivalence of categories of maybe some kind of bounded and complete filtrations with vector bundles over A. And similarly, if we have a vector bundle over A cross X for a scheme X, that's going to be a filtered vector bundle. So now suppose we're given a smooth projective morphism. Then we get a morphism of Hodge stacks that fits into a pullback diagram like this. So X Hodge maps to S Hodge. Now S Hodge, as we sort of saw before, it's a quotient stack of A cross S, which is to say we took A cross S and we just added a formal groupoid structure. So when you add a formal groupoid structure, the stack that represents it receives a map from just A cross S itself. In other words, A cross S is the object of the formal groupoid. So we can then just make a pullback diagram, and we'll just define that to be X Hodge over S to be defined to be the pullback of this map. We're doing that just so that we can turn stuff into things which are actually happening over a geometric looking space like a scheme, basically. As I said, this is really basically A1 cross S with the GM equivariance. And so then we can take cohomology vector bundles. So we can take the higher direct image along this map. Let me just back up for a minute. We can take the higher direct image along this map here, okay? So that's RIF Hodge over S lower star of O. So that's a bundle on A cross S. The fact that it's a bundle, that kind of already contains much of the stuff about degeneration of the Hodge to Durham spectral sequence and stuff like that. I mean, a priori, if you do this for just kind of anything, a priori, you might not expect that the dimensions of the fibers over 0 and 1 be the same. But that's the fact that the spectral sequence degenerates, so the Durham and the double cohomology have the same dimension. So the fact that this is a vector bundle, that already contains that information. And furthermore, this sheaf on A cross S, if you just look at its definition, right, it comes from pulling back the structure sheaf here. We take the direct image of the structure sheaf. That's obviously just the same as taking the direct image of the structure sheaf from here down to here. So since this was just a pullback, the direct image over here is just the pullback of the direct image here, which is to say that our sheaf on A cross S has a descent down to S Hodge, or in other words, it has an action of the S Hodge formal group scheme, formal group. Okay. Now the fiber over 1, if we restrict to 1 cross S, it's just the relative Durham cohomology of X over S. And the fact that it has a descent down to S Durham is the Gauss-Manin connection, right? The S Durham is the fiber of S Hodge over 1. The fact that this has a descent down to S Durham is the Gauss-Manin connection. So let me say hello if Elaine is, I don't know if she's listening, but I first learned about this in one of her papers.
Yeah, sure, I'm listening.
Okay. Anyway, so thank you. So
I mean, how would I not listen to your lectures? There's no way.
Okay, so anyway, so this is Elaine's paper, I guess probably with Eckhart was where I learned about this first. So, there's usually a nice, argument using connecting map in the, with a short exact sequence of hypercohomology complexes.
Well, I mean, that's a viewpoint of Nick Katz. Yeah.
Yeah, I guess so. But you guys explained it in one of your papers in any case.
Oh, okay.
And yeah, but we can just, in a formal sense, that just comes from this picture that this Durham over S just has a descent down to S Durham. Okay. And now also we have a structure of a bundle over A cross S. So as I was saying before, when you have a vector space, when you have a bundle over A, that's the same thing as a vector space with filtration. And if we have a vector bundle over A cross S, that's the same thing as a bundle over S with a filtration. And the fiber over 0 is the associated gradient of that filtration. And that structure of a bundle over A cross S is the Hodge filtration on the Durham cohomology. And now the fiber over 0 is the associated gradient of the Hodge filtration. So it's what's called now, I think, the Hodge bundle So this shows up a lot in Kong's work, for example. This is the Higgs bundle associated to the connection, and it comes from the associated gradient of the Hodge filtration. So V0 is just direct sum HQ of X over S coefficients omega P X over S. And this was, I first learned about this really in Griffith's courses about Hodge theory. This was a standard object that we were looking at in Hodge theory. And the fact that we have a descent of the entire picture to S Hodge, this encodes the relationship between the Gauss-Manin connection and the Hodge filtration, which is to say it encodes the Griffiths transversality relationship. And that's going to tell us that the action of the S Dolbeault formal groupoid on V0 is the Higgs field that you get in classical Hodge theory from HQ, I've got this, right? HQX over S omega P into HQ plus 1 omega P minus 1 tensor omega 1 S. And that's what was usually known as the Kodaira-Spencer map. Okay. So in usual Hodge theory, this map is given by cut product with the Kodaira-Spencer deformation class, right? Our family of varieties has a deformation class, which is a section of the relative H1 of X over S with coefficients in the tangent bundle. So the full family has the deformation class as a section of that over S. And if we go back this map from here to here, that's just cut product with the deformation class, right? It's a class in H1 of coefficients in the tangent bundle. So the H1 term that makes Q go to Q plus 1, and then the tangent bundle term contracts a P differential and gives you a P minus 1 differential. Yeah, I'm sorry, this was a mistake. We need to tensor with omega 1s here. So at this point here, we need to tensor with omega 1s, I'm sorry. So this omega 1s here, that's supposed to appear. I could tech this right away, but let's not do that. So there's there's an omega 1s, which should go right here, okay. Clearly. Okay, so now we know from Griffith's theory that if phi equals 0, if the Kodaira-Spencer class equals 0, then the variation of Hodge structures is locally constant. This tells us that the Hodge filtration on the cohomology spaces stays invariant, which tells us that the period mapping is constant, and it almost tells us that the variation of Hodge structure is constant. However, there could still be a finite global monodromy group in Griffith's theory, or well, let's say a unitary in the complex variation of Hodge structure picture. And so what's known as the infinitesimal Taylor property is the statement that if phi equals 0, then psi equals 0, right? Of course, if psi equals 0, then obviously phi equals 0 because phi is the cut product with psi. But the infinitesimal Torelli property is an injectivity question going back in the other direction. So that's just a doubly touristical comment to situate things. Some of you might be familiar with this property, so that's why I said that. So now so what we would like to do today is we're gonna look at a situation where phi equals 0. So the Kodaira-Spencer class is actually 0, but the family is not isotrivial and it's gonna be over a higher dimensional base. And the idea is to try to detect this by a secondary or higher Kodaira-Spencer map for the Hodge filtration in nonabelian cohomology. So this is I'm mostly using this as an opportunity to review this nonabelian cohomology stuff. Let's put it that way. Okay, so let's recall the general framework for nonabelian cohomology, at least one possible general framework for nonabelian cohomology using n stacks. So if X over S and T over S are n stacks of n groupoids, and n could be infinity here, over a base S, the S could also be a stack as well. It's the S Hodge, for example. Then we have a relative mapping stack, which is just Hom from X over S into T over S. Okay, that's a stack over S. So we can write the formula in this way. So it's if we have a scheme over S, if we have a scheme mapping to S, then we take the fiber product. We pull X and T back to R. We look at maps from X cross R into T cross R. And then but we only look at those maps such that they're compatible with the projection. That is to say, the map from X cross R to T cross R and then mapping down to R, that's the same as just the second projection from X cross R. So this is just what you would think it would mean, okay? But the point here is to write this down, and we can write this down in a formula like that, which makes it work for any kind of n stacks. Okay. Maybe I should say, so what's an n stack? I mean, it basically means a simplicial presheaf over the side of schemes over K. That theory is now pretty classical since we've translated by a certain number of decades. But we view this, so this is just kind of a philosophy. We can view this as, we'll call this the non-abelian cohomology of X over S with coefficients in T. What we'll do today, T will be constant over S, okay, but it could be non-constant. So if we set T equal to the K, so this K OSI, that means the Eilenberg-MacLane stack for the sheaf of abelian groups OS. So this is a stack whose homotopy group stacks are equal to OS in degree I and equal to 0 in other degrees. The theory of n stacks kind of tells you that those are the homotopy group sheaves. If you take the homotopy presheaves, they're not that, because that involves cohomology. But if you take the homotopy group presheaves of this simplicial presheaf and then sheafify them, then you're supposed to get 0 except in degree I. So there's an Eilenberg-MacLane stack like that. Then we apply the truncation or the pi 0 to all of our answers. Then we just get back to the usual relative ith cohomology with coefficients in O that we saw before. Did I put? I didn't put. But so that's why this is why we're going to call this non-abelian cohomology, because if we took kind of an abelian space here, then we just got back to the usual abelian cohomology. Okay, so just in formal terms, the previous discussion of Hodge filtrations, Gauss-Manin connections, Griffith's transversality, and everything carries over perfectly well in this context. We can just sort of replace cohomology with this non-abelian cohomology. We need some conditions on T to ensure that the answers that we get are actually reasonable. And one sort of criterion for being reasonable is that we should have an analytic Riemann-Hilbert correspondence between the de Rham cohomology and Betti cohomology. So what we'll do here, we'll take the case where T is constant, which in other words, it doesn't vary over S. But we could envision to have a cohomology with coefficients in a variation of non-abelian mixed Hodge structure over the base S. So let me just make a little aside remark on our paper with Kodaira and Pantev on non-abelian mixed Hodge structures. We're not going to use these today, but anyway, I should comment on this. So in our paper with Kodaira and Pantev on non-abelian mixed Hodge structures, then we're talking about having a Hodge filtration and a weight filtration on the coefficient stack itself. Okay, the Hodge filtration would be something like what we'll see below. The weight filtration was more mysterious to us at the time, and I don't think we've improved that situation since then either. So we proposed having an additional commutativity structure on the associated graded part of the weight filtration. That seemed to be necessary in order to make it coincide with what we know for rational homotopy theory, for mixed Hodge theory of rational homotopy theory. And at the time, derived algebraic geometry was just in its infancy, and we weren't able to use that. But we speculated that you should actually use derived algebraic geometry to understand the weight filtration. In other words, that our coefficient stack T should not just be a stack, an n stack, but it should be a derived n stack. The advantage of a derived n stack is that we have this hidden smoothness property. So we can sort of pretend in a formal sense, at least, that it's smooth. And that's going to maybe improve some questions about the weight filtration. So I think there's, if I'm not mistaken, I think that Mauro Porta has some current ongoing work going in this direction, but I'm not sure what current status is. So anyway, we're not going to talk about the weight filtration today any further. And we're also going to not have a specific different Hodge filtration on our coefficient stack T. We'll just have a stack rather than a Hodge filtered stack. Okay. So now here's how we can make a good set of conditions on our stack. So we'll take T as this, I'm sorry about the terminology, this wasn't very good, but a little bit historical. We'll call it connected very presentable if pi 0 is, so being connected means that the pi 0 sheaf of T. So let's recall it. So this means that T is going to be an n stack on the side of schemes over K. So T is really a simplicial presheaf over on the side of schemes over K. Okay, so as such, it has homotopy group sheaves, which are themselves sheaves of sets over the side of schemes over capital K. So it makes sense to say pi 0 of T equals star. That just means as a sheaf of sets, it's the 1-point set. It also makes sense to say pi 1 of T. I didn't put the base point here, which is a bit of a question, but if pi 0 of T equals star, then kind of locally there's only a unique base point. So this is roughly speaking well defined. So pi 1 of T should be an affine algebraic group, right? It's going to be a sheaf of sets with a group structure. And we ask that it actually be representable by a group scheme, an affine group scheme. In particular, for example, putting an abelian variety here doesn't seem like a good idea. I mean, I guess you could try that, but that's going to give something a little bit different. Anyway, so that the conditions that G is an affine algebraic group, finite dimensional, let's say. And for I bigger than or equal to 2, the pi I of T are just additive groups. That's the easiest possible thing we could have, which is to say the sheaf represented by the additive group scheme is just O, is the structure sheaf. So we're just asking that these things be, finite dimensional vector spaces, tensor with the additive group. And viewed, and this should be an algebraic as a representation of, I think that's automatic, but let me say that. Algebraic as a representation of G. I mean, if G as a sheaf of groups acts on GA as to the R as a sheaf of groups, then that's going to be an algebraic representation. But so this part of the data is relatively simple. It just means, right, we just have a group and we have some vector spaces which are representations of the group, basically. There's just some connecting stuff. There's some classes that tell you how this stuff adds together, basically. In this case, so our criterion, one of our criteria was that we should have a Riemann-Hilbert correspondence, and there's a Gaga principle with the Holt, and we get a Riemann-Hilbert correspondence. So in our case where X was a smooth projective variety, then we have this principle that Hom from X Duram into T for a stack T of this form. The analytic stack associated to that is equivalent to the analytic stack associated to Hom from X Betty into T, where X Betty is the constant infinity pre-stack, which associates to any scheme. It associates the infinity groupoid, which is just the topological space of X. Okay, that's a pre-stack. So if you wanted to take the associated stack, that would modify that a little bit, but it's not going to modify it a lot actually, because in the Zariski topology, there's not going to be a lot of different maps from the Zariski topology into this topological space. But once we take the associated infinity stack, for example, its value on the empty set is going to be a point rather than X Betty, than X top. Its value on a disjoint union is going to be a product of things rather than just constant. Anyway, so that defines our Betty stack. Okay. And there's also, we could also make, I'm not even sure, I said there is, but I'm not even sure I've really written this down, but you can make a relative version on X over S, but then the Betty stack on X over S, that's going to be the local system of topological spaces over S. So for that, you're going to need the analytic topology in S, basically. So in order to make this, you would have to say something about the analytic site over S analytic.
And sorry, maybe you said this already, but does X have to be smooth projective or something for this?
Yeah, X for this Gaga principle, X is smooth projective. Yeah. So for example, I mean, that's a good question. So for example, if X is quasi-projective, at this point, you can already see that we're going to get something slightly different. This kind of shows up in my paper with Konstantin, my quote paper. Which is to say, in this case, we're going to get local systems, right? We're going to get, vector bundles with integrable connection over X, right? That's not the same as representation because you can have wild representations, right? So if we take X to be quasi-projective already at this point, we would have much more stuff which corresponds to local systems with irregular monodromy, with irregular singularities at infinity. So I think if you put, I think we maybe said this with Constantine. If you make a regular singularity condition, then maybe we can get back to a statement possibly. Let me not say anything definitive about that. Okay, so now let's just write it down, everything. We'll just recopy what we did before. So if we have a smooth projective morphism, I guess this kind of answers your question, Remy. If we have a smooth projective morphism x to s, then we get the same diagram. I just recopied the diagram. It's a little bit shortened. Right, we have x Hodge mapping to s Hodge and x Hodge over s mapping to a over a cross s and so on. And then we can take the relative non-abelian cohomology stack. So that was why I was talking about the relative cohomology stack before. Let me just back up here. That was why we put this definition here, right? In terms of this definition here, I'm envisioning T to be a family over S, whereas in the application here, T is just a single thing, which is to say it's a constant family over S. One should be able to take the case of a non-constant family, but as I said, that's going to involve defining some kind of good notion of variation of non-abelian mixed Hodge structure over S. So let's just take a constant family. So we have the relative Hom x Hodge over S over A cross S. This is a stack which maps to, which lies over A cross S. So this is a stack on A cross S, but it has a descent down to S Hodge just because we could have made the same definition on this side. Okay. But geometrically, it's maybe a little bit easier to think of a stack over A cross S that has a descent down to S Hodge. And now as before, a stack over A cross S amounts to a filtration, but where here the definition of filtration is being a stack over A, right? So we can just define filtration of a non-abelian of a stack to be something over this A. Okay. So this is just terminology, shall we say? But that's what we'll call the Hodge filtration on the relative Durham cohomology stack. Okay, so the fiber over 1 is going to be the Durham cohomology stack, which is Hom of x Durham over S into T. Okay. Let me recall, that's the thing which showed up here, right? I guess here we don't have a base, but that's what showed up here to have the Riemann-Hilbert correspondence. Okay. Now the fact that this relative Durham cohomology, which is a stack over S, the fact that it descends down to S Durham, that's the non-abelian Gauss-Manin connection on the relative Durham cohomology. And if we go back to the comparison of the Betti cohomology, it's going to correspond to a locally constant structure on the Betti cohomology. Then we have a full descent of the whole filtration from A cross S down to S Hodge, and that's just going to be the Griffiths transversality statement relating the Gauss-Manin connection to the Hodge filtration. Okay. So, and then if we specialize to the Dolbeau fiber, we get a relative non-abelian Dolbeau cohomology, which is Hom of x Dolbeau over S mapping into T. That maps down to S, which is the 0 fiber of it over A cross S. And so what used to be the Hodge filtration is now an action of the multiplicative group. Okay. So the residual part of the Gauss-Manin connection is going to be a descent of this down to a formal groupoid S Dolbeau, right? And in this case, the formal groupoid it's not really a quotient of S, but it's really the classifying groupoid over S of the tangent bundle. And as I said before, it's really the classifying groupoid of the completion of the tangent bundle along the 0 section, but we can ignore that distinction from now on. So we can just view this as an action of the tangent bundle TS on this stack, on this relative Dolbeau cohomology stack. And that action should be compatible with the GM action. Okay, so now let's just specialize to the case of BG coefficients. So if we have an affine algebraic group G of finite dimensional, then we get the usual, so I mean, this whole theory was just envisioned as a generalization of this one-dimensional non-abelian cohomology theory, which we already knew about. That's why I think it might possibly be relevant for the conference here, because we've been talking about some one-dimensional non-abelian cohomology. So maybe some things might generalize possibly. So if we take the X gram, then Hom from X gram into BG, that's just the moduli stack of flat G bundles, which I guess sort of appeared first in maybe Deligne. Helen maybe would have a comment on this, but I think that the idea of having a family of connections parameterized by a base scheme, I think that shows up in some of Deligne's earlier papers.
There are so many things showing up in Deligne's works that
yeah.
I can say for sure. But I mean, it's a good guess.
Yeah, I think it roughly speaking shows up in the lecture notes.
Yes, because yeah, he's looking at the behavior of residues in families, for example. Yeah, sure. Yeah. Okay,
so now if we take the X Dolbeau, let me just allow myself to use the Dolbeau. I usually put an MH now because this is due to Hitchin, but let me call this Dolbeau for today. So if we take the Hom from the X Dolbeau into BG, then that's the moduli stack of G Higgs bundles, defined by Hitchin. We should also impose some semi-stability and vanishing term classes here. So if we just take the moduli stack of all Higgs bundles, that's going to be sort of too big to fit into any kind of non-abelian cohomology picture. So I mean, you could if you want, but it's better to impose some semi-stability and vanishing term class conditions. And in particular, if we talk about the Hodge cohomology, then we should impose those conditions on the zero fiber. Okay. And so, Ellen, I don't know if you saw my comment in the conversation of your talk, but this is due to.
I saw afterwards. So thank you very much. Of course, you're right.
Yeah, this is due to Lubotsky-Majid, at least for the GIT theory. I'm sure you could say that people have been looking at that for centuries, maybe. You know, it goes. There's a.
Yes, thank you for the comment.
Anyway, my only contribution here was just to call this Betty, right? To call this Betty cohomology. Anyway, so this is the Hom from X Betty into BG is just the moduli stack of G representations of the fundamental group. Maybe introduce is not exactly the correct term here, but Lubotsky-Majid did the GIT theory to get the coarse moduli space for that core moduli stack. Okay, and so we get back the usual structures of non-abelian Hodge theory for these stacks. Okay, in particular the Hodge filtration and the Gauss-Manin connection. So now what are we going to do? We're going to just look at another case, which is the two-sphere considered as a three-stack. But so let me just comment. It's undoubtedly an interesting question to look at the case where T involves both, as I was saying, both the group in degree 1 and the higher pieces also. But today we're just going to take a different tack, and so we're not going to look at the group G. We're just going to take pi 1 of T is trivial, and we'll look at the next non-abelian case where T very simply corresponds to the rational homotopy type of the two-sphere. So let's recall, I didn't write this here, but let's recall that the rational homotopy groups of the two-sphere, there are only two of them, pi 2 and pi 3. They're both equal to Q. In other words, the homotopy groups of the two-sphere, there's a pi 2, which is Z. Pi 3, I think it's also equal to Z. And the higher pi i's are all finite groups. We don't know what they are really very well, but they're finite groups. So the rational homotopy that's two. I heard a very interesting talk here at the Institute, I think by Tony Feng, if I'm not mistaken, about Steiner operations in over characteristic P. So I think if our field was not of characteristic 0, but of characteristic P, then who knows what's happening? I mean, this is bound to be interesting. But anyway, for us here, for me, we're just in characteristic 0. So if we tensor our homotopy type of the two-sphere with our field, and this should more precisely be saying we're tensoring it with the structure sheaf on the side of K scheme. Then since the characteristic of K is 0, it only depends on the rational homotopy type of the two-sphere. So there's going to be only two non-trivial homotopy group sheaves, pi 2 and pi 3. Those are both just a single copy of the additive group. Okay. I think there was a paper by Breen and I'm forgetting the name, Ekadal, about the schematic homotopy type of the two-sphere. But this is just an easy case of that. So we're kind of talking about schematic homotopy type here also. Obviously, there's papers of Bertrand, Toen, and Bitsozi and other people. But we're just doing something simple, which is in characteristic 0, we're tensoring. Okay. So that's just going to be the same as taking rational homotopy type. So now the idea is we're going to use this as our two-stack. This is our cohomology stack, it's a 3 stack. It's a 3 stack, right? Because the pi has up to pi 3. And so the Poisson-Markov tower of the stack is a fibration. So it's a fibration. So T maps to K0, KO2 because pi 2 is O. And the fiber is KO3. Okay. And that's the structure of T. And it's given by a non-trivial classifying. There's a classifying element. There's something called Breen calculations that calculate the cohomology of this stuff. And using those calculations, you can just say what the classifying map is. But we'll just describe this in a minute more simply. So we can just describe this in maybe a little, without just talking about the classifying map for this vibration. We can just say, we can say that a map from Y, from a space Y into T, is the same thing as a map from Y into KO2. That's to say, a cohomology class. So if we take the global sections over the side of schemes over K, then that's just a coefficient K cohomology class in H2 of Y. Here we're just talking about singular cohomology, okay? Plus a trivialization of its cup product. So that means a class psi, a 3-dimensional chain such that d of psi equals eta cup eta. And the fact that there's a choice of psi here, you can modify psi by a closed 3-dimensional cocycle. That's reflecting the fact that the fiber of this vibration is KO3. But this is an affine equation. This is not a homogeneous equation, right? So psi is not itself an element of 3-dimensional cohomology. Okay.
I'm a little bit confused. Didn't you tell us earlier that KO2 classifies the H2 of Y with values in O instead of K?
Yeah, so maybe I should have said that, but what I wanted to put K here. I mean, that's why I said if we take the H2 of Y with coefficients in O and then take global sections over the side of schemes over spec K, then it's just going to be H2Y K. But you're right. I mean, I should have written maybe O here, but that might be a little confusing. I'm just trying to make this look concrete in topological terms. I mean, if you just look at maps from Y into the rational homotopy type of the sphere, it's going to be a rational cohomology, a Q-valued cohomology class of Y, and a trivialization of the cup product over Q. But yeah, thank you. So you might want to put an O here. And so we would like to look at the relative Dolbeault cohomology. So to get down to our example, we'd like to look at the relative Dolbeault cohomology for a family of varieties, X over S, smooth projective and so on, with coefficients in T. And the base is going to be a higher dimensional stack dimension 2. You'll see in the example in a minute. As we explained before, the relative Dolbeault cohomology comes out as the associated gradient of the non-abelian Hodge filtration on the relative de Rham cohomology. Fits into that big picture that we said before. And we have a Kodaira-Spencer map, which is to say an action of the formal groupoid tangent space of S. Okay, so I mean, maybe this wasn't written quite correctly. It really means that we have, I mean, I should really maybe write S mapping to here, right? We have a descent of our thing to having to being something over KTS. So in other words, our Dolbeault cohomology is really, it's really something that lies over KTS. Which is to say it's something that has an action of the group scheme TS. Okay. Something over S, but has an action of the group scheme. And the key point of what we're going to do here is that this is the action of a commutative group of higher rank, because where I said dimension of S equals 2. So if you have a commutative group of higher rank, then an action of that group on something has cohomological invariance, tends to have non-trivial cohomological invariance, just because commutative group has cohomology, right? If you take a free group, a free abelian group has cohomology. A free group has no higher cohomology, but a free abelian group has cohomology, and indeed hi of q to the r. Q is the ith exterior power of q to the r. Okay, that's just in the usual topology. So now we have an Artin 3 stack. So our relative Dolbeault cohomology with coefficients in T is going to be an Artin 3 stack, okay, over S. I didn't check. I suspect it might only be a 2 or a 1 stack, but anyway, a priori it's an Artin3 stack because T is a 3 stack. And it's provided with a morphism to the vector bundle over S, which is just H2, right? If I put, remember what we said, if we put, instead of T, if we put KO2 here, then the mapping stack is just, well, it's a higher stack, but it's pi 0 is just going to be the H2 Debye cohomology, right? The H2 Debye cohomology has these 3 pieces, okay? And so the image or a map from H into this H2 Debye cohomology is the family of cones of cohomology classes eta, such that eta cup or eta wedge eta equals 0. Okay? So we have a stack which is mapping to this Debye cohomology space, and its image is the set of classes such that eta cup eta equals 0. And now our Kodaira-Spencer datum is going to be an action of the tangent bundle on this stack H relative to S. Okay. Now in our example, so we're going to make an example where the variation of Hodge structure for the family is going to be constant, as you'll see in a minute. Therefore, any first order Kodaira-Spencer classes are going to vanish. Which in terms of the action, it means, maybe let me go back, well, let me just say, in terms of the action, that means that the action of any given tangent vector is trivial, okay? So we have a tangent space, dimension of x is going to be 2. So there's 2, at any point there's 2 tangent vectors. The action of any one of those tangent vectors is just the usual Kodaira-Spencer class. That's going to be trivial, okay? So we basically have an action of a commutative group with 2 generators such that the action of either one of those generators is trivial, okay? But that doesn't mean that the action is trivial. So what we're going to say here is that we get a second order Kodaira-Spencer class, which is going to be a function from lambda 2 TS into somewhere. We'll see that in a minute. Where's that somewhere? Let's see. So, well, we'll see that in a minute in the next slide, I think. But let me just say, so we're going to choose our class eta. We're going to choose it inside H11. And we're going to choose it so that its cup product with itself is 0 in H22. And we're all in our example, we're also going to have H3 equals 0 so that the solution of deep psi equals eta cup eta is unique, which is going to basically mean that we have an injection from pi 0 of H is going to be injecting into H2 double of x over S. So now let's go back to figure out where this obstruction, where this higher thing lands. I would claim that it lands, so we have an action of a commutative group scheme, TS, on a stack H. This is all over S. The action on the pi 0 is trivial. And then I claim, plus maybe I should say, sorry, I should have said here, we're also assuming that the action of each vector is trivial. Okay, so, and then the secondary class based at a point is going to be a map. A map like that, basically, okay. So what are we saying in topological terms? So the thing is, when you're thinking about these higher stacks, you have to always be thinking about topology, because higher stacks is just topology relative to the site. So, relative to a point, it's just topology. Okay, so we have to think in terms of topology. So let's think about that for a minute. So it means we have an action of a commutative group Z2. And here it's the tangent space of S, but you remember S has dimension 2, so its tangent space is a rank 2 abelian group scheme. Okay. But so in terms of topology, suppose we have a map of an action of the commutative group Z2 on some space H, which is going to be our stack here. But suppose we just have it, just forget about all this stack stuff, right? Can rest your minds a little bit. Suppose we just have an action of Z2 on a space and it fixes some connected component. Okay, then I claim that we get a map. So maybe I should have said something about the trivial action of, but I think that that's automatic. Then we get a map from wedge 2 of Z2 into pi 1 abelianized of H. So that's going to be the obstruction to having an actual homotopy fixed point of the action. A homotopy fixed point would be an equivariant map from R2 into H. And so if you want to define so let's think about this a minute. If you want to define a homotopy fixed point, what would you do? You would take the fundamental region, right? So if we know that the base point gets mapped by each of the generators, gets mapped to some other point in the same connected component, then we can choose a path, okay? So that's going to give us a map from the boundary of our fundamental region into H. And the question is, can we fill that into a map from the fundamental region into H? And then we can just copy that a zillion times and get a map from R2 into H, okay? There's going to be an obstruction to that. That obstruction is obtained by the loop that you get by going around the side of the fundamental region. If you think about it, I'm pretty sure that obstruction is actually lies in the pi1 of h abelianized, because if you change the path by something, then that's going to, if you change each of those two paths by something, that's going to change the full thing by the commutator. So it's the pi1 of h mod the commutator. And so let's just illustrate this, the possibility of having a non-trivial action. So you might say, why is that non-trivial? But let's just illustrate this. So I would claim that everybody knows this, in fact. If we take a non-trivial circle bundle over a two-dimensional torus, so we take the unit circle bundle of a non-zero degree line bundle over an elliptic curve, if we pull back to the universal cover, which is R2, then we get an action of the fundamental group, which is Z2, on the universal cover. We get an action on the circle bundle over the universal cover. Well, the circle bundle over the universal cover is homotopically S1. So we get an action of Z2 on a space which is homotopically S1. It doesn't have a homotopy fixed point, because if it did, then that would give us a section of this circle bundle, which for a non-trivial degree line bundle, it doesn't have a section. So that's just an illustration to show that you can have, an action that has a non-trivial class. So what we're just doing here is we're sort of finding a class like that in Dolbeau homology. So let me just say, here's the example. So the example is we take a simply connected smooth projective surface, and let's assume, and we're going to assume that H0 ZKZ that that has a non-trivial PG, I guess. Right, we're going to assume that H20 is non-zero. Then that's going to be the base of our family, and the family is going to be blow up the diagonal of Z cross Z over S. Okay. In other words, the base of our family is just, we take Z itself and the fiber XP over a point in Z, that's just the blow up of Z at that point P. So we're just going to be blowing up the same surface at a moving family of points. So that's going to be our family of varieties. So you can see that automatically that's going to have trivial variation of Hodge structure, right? So there's no variation of Hodge structure. There's no first order Kodaira-Spencer map. What I would like to point out here is that we are going to have a higher order Kodaira-Spencer map, second order Kodaira-Spencer map. Okay. So X over S is the family of blowups of Z at the moving point. So X, the fiber over a point P is just the blowup of Z at the point P. Okay. Well, let's let EP be the exceptional divisor in the fiber, and let's let E be the exceptional divisor of the total space. And we choose a coefficient C with the property that C times the hyperplane section. I didn't want to use H because we've already got a lot of H's here, but C times the hyperplane section plus the exceptional divisor should have eta cup eta equals 0 in each fiber. Right? This is going to be a class in H11. Okay. I should have said the term class of this whole thing. So this C is a constant, not a term class, but you would also take the term class. So the term class this is a class in H11. So it gives you and since we have eta cup eta equals 0 in each fiber, and remember I said that we're going to take Z as simply connected surface, so the H3 and the H1 are 0. So we get a section of H pi 0 of H, our non-abelian cohomology classes over S. We might not be able to choose a constant inside rational cohomology, which is to say we might not really have a map of topological spaces, but I mean, it would have to be integral to get an actual map, but anyway. But we're going to still have a map into this schematic homotopy type tensored with K. Okay. The variation of Hodge structure for our family is trivial, as I said before. When we blow up a moving point, we don't change the variation. We don't change the Hodge structures. And so here's the calculation. So this was done a long time ago. It was pretty complicated, and I think it should be done better, but haven't done that recently. Anyway, so the result of the calculation is that the pi1, so remember that the classifying map takes values, that the obstruction map kappa takes values in the pi1 of the stack. And you can calculate, that's going to be the Dolbeau cohomology modulo the class generated by eta. And it turns out that our secondary class in the calculation, it actually goes into the H02 part. Since eta was in the H11, then that we don't care about the mod eta thing, right? The kappa obstruction class goes from the second exterior power of the tangent of the base into H02 of the fiber. I probably should have erased that P here. I mean, this should be xp, okay, if we want to take the value of the point p.
Can you say again what is P here?
Well, p is our point inside the base S. So there's something wrong. Sorry.
If you look at the fiber here, you should look at the fiber on the right-hand side, right?
Yeah, we should put a fiber here. So we should either put p over here, or we should remove the p here. Okay, one of those two.
Okay.
Sorry about that. But anyway, that's what I just put that there. I think I put that because that was the calculation I wanted to do. So the tangent space of S at the point P is just the tangent. I mean, S is equal to Z, so it's the tangent space of Z at the point P. And so I should have a P here again. Well, I mean, H2 of X over S, comma O is just H2 of Z. It's a constant sheaf over S. So anyway, sorry about that. So anyway, the fiber of that over the point P is always just going to be H2Z OZ. Okay. And by Serre duality, H2Z OZ is just H0 of Z omega 2Z dual. And we have evaluation of forms at the point. So forms at the point evaluate. That gives you a map from H0 of Z omega 2 into the second exterior power of the tangent space at Z dual, right? Because the tangent space is dual to the omega 1. Okay. So I think now we're down to a correct formula, at least with the P and the so on. So, right, evaluation of forms at the point P gives you a map like that from H0 of Z omega 2Z over to here. But by Serre duality, this space here is the dual of H2 of Z OZ. So if we take the transpose of this map, then the transpose of this map is a map from the second exterior power of the tangent space of Z at the point into the dual of H0 omega 2Z. I should have said that's equal to this other space. That's equal to this space. Okay. And so the theorem of the calculation is that up to some constant, the non-zero constant, the transpose of this map, kappa, is the transpose of the evaluation map. And so under our hypothesis, it's non-zero for a general point P. So that's our illustration. So to conclude, that's our illustration of a case where we have a family of varieties, a kind of simple family of varieties, but Z has to have non-trivial holomorphic 2 forms on it. We have a family of varieties, and we move the point P inside the varieties, and we blow up that point. I'm sorry, we have a family of varieties obtained by moving a point P around in a given surface and blowing up those points. And that clearly has trivial variation of Hodge structure, so it has clear trivial Kodaira-Spencer map, but it's going to have a non-trivial secondary Kodaira-Spencer map. That's the conclusion of the calculation. So I guess I think you have to wonder, yes?
That's the same thing as blocks decomposition of the diagonals. That's the same computation.
Quite possibly, yeah. I think this should clearly be related to this, to the question.
That's a variational part of the class, of the Durham class in that case, of your zero cycle.
Yeah.
As you move it. So
right. So I guess what we're saying here is that we can interpret this as a Kodaira-Spencer class.
Yeah. Okay. Thank you.
That's maybe, so I'm not sure whether this is what I'm saying here, but anyway, this is the, oh, it's just, right? So thank you then. I think we can give the following interpretation, right? The Leray spectral sequence for the fibration degenerates. And so we have a class such that the eta cup eta is equal to 0 in H0 of S in the term H0 of the base with coefficients H4 of the fiber. That does not guarantee that there's a global class with self-cut product equal to 0. And the next level is H1 of the base with coefficients in H3, but we made the hypothesis that that vanishes. And then the next level is H2 of the base with coefficients in H2 of the fiber. And this is going to have a term in double homology, which is H0 of the base with coefficients in omega 2 tensor omegas H02 of the fiber. And I think we can guess here that this is the same as the class we calculated here. So I'm not sure we really gained too much by this, but I think we gained just a teeny bit, which is that we show that it's only depends on the second order infinitesimal neighborhood of the deformation, whereas this class is a priori global. And so I should also say, I'm pretty sure, but again, I didn't do this, that this class should be expressible as a Massey product of 2 times eta. I mean, if we take a wedge product alpha, wedge beta here, then it should be expressible as a Massey product of eta, eta, alpha, beta, basically. Anyway, okay, so I'm done. So finished.
Okay, so thanks for your very nice talk. So any questions or comments?
Can you say what is alpha beta in your last comment? You said eta, eta, alpha, beta. So what are alpha and betas?
Just alpha, beta are sections of the tangent bundle. Locally on S, if we take two different tangent vector fields, then the source of this map is a wedge 2, so it's going to be of the form alpha, wedge, beta.
Okay.
I'm saying that the image of alpha, this map takes alpha, wedge, beta, maps to, the guess is that that's going to be the fourth Massey product, eta, eta, alpha, beta, basically. Having the third Massey product maybe vanish because of our hypothesis that H3 vanishes.
Is there an example where you would expect to see a triple Massey product show up via one of these higher Kodaira-Spencer classes?
I guess there should be. That's a good question. Well, I mean, it might be. I mean, there might be two different possibilities. I mean, you might either do some kind of non-abelian. There maybe there's a case where there's some kind of non-abelian cohomology, but right, which is going to have this Positnikov decomposition, but where the Kodaira-Spencer operation on each of the terms of the Positnikov decomposition is trivial, but somehow the Kodaira-Spencer class on the combined non-abelian cohomology is non-trivial. Then that would be sort of a alpha wedge, eta wedge, phi, or something like that, a Massey product. Or you might also have a situation, maybe but let's see, that's a little less likely that you would have a single eta and two alpha wedge, beta, wedge, eta. I'm not sure I would see an alpha wedge, beta, wedge, eta showing up, but you might see an alpha wedge, eta prime showing up if you had a. I mean, I kind of made I'm making some hypotheses here that like there's no H3 involved or something like that.
I guess you could also look for a situation maybe where you had like a non-commutative deformation, and then no, that's in the wrong. Never mind, it's in the wrong degree. Sorry. Yeah,
but there should be deformation. I mean, I was trying to here to get an example where the first order Kodaira-Spencer was 0, but you should be able to have an example in non-abelian cohomology where the first order Kodaira-Spencer is non-zero, and I guess that's just a guess, but that might be a triple Massey product. I mean, I think. I mean, looking back over this, clearly, I mean, I should have done more, obviously, but I got tracked into other things basically. But one obvious thing to do is to try to just develop this Massey product thing in a more systematic way to explain why these classes are just given by Massey products. That should, in general, be true, basically.
Thank you.
Yeah.
So, more questions? Maybe I have a question. Yeah. So suppose we have a smooth family over a base smooth family, but suppose the usual variation of Hodge structure attached to the family become trivial, but is it possible to apply this kind of variation of a no-abelian Hodge structure to get something more? Yeah, to see something about the base with large pi 1 or hyperbolicity, although the usual variation Hodge structure is trivial, but try to apply this kind of no-abelian variation of no-abelian Hodge theory.
Yeah, I mean, well, okay, it's going to have something to do with some kind of higher cohomology class on the base, but that wouldn't necessarily preclude having something about the fundamental group of the base, because maybe the group of the base has, some higher cohomology classes or something.
Okay.
So I think it should be possible to have an example also where you have a moduli space of local systems, and then you have a stack T that has a G and then has some higher stuff, and maybe have some cohomology classes. So there might be, for example, cases where the Kodaira-Spencer class is some kind of cohomology class over the moduli space of local systems with coefficients in a natural bundle. I mean, so maybe one thing should be pointed out here is that if we take the case where we take pi 1 if t equals g, and we just take pi some other I, and pi I is some, is a representation of g, but we don't have several levels of pi. We just have a single other pi I. Then that's basically going to give you the, the kind of the cohomology jump loci picture over the space of local systems. The cohomology, the non-abelian cohomology stack is going to map to the H1 moduli stack. And the fiber is basically going to be the cohomology with coefficients in that associated local system. So that's going to be maybe like a perfect complex over the base. Fiber is the cohomology of that local system. So I think you could ask whether there's some kind of higher Kodaira-Spencer situation inside there. I didn't look at that either. But I think you might expect that could possibly exist in any case.
Okay, thank you. Thank you. So any more questions? Okay. If not, okay, thanks again. Yeah.